I don't have time to process this video, so you're going to see me flipping out of this. I usually cut this piece off. I made a video and it wasn't recording sound, so here we are. So here are my topics for the freestyle: factoring basics, and I guess this last thing's kind of a different topic, the intermediate value theorem. So just to recall that this is the form of a quadratic where ax squared plus bx plus c, um, where a is actually a number. And so you might be able to factor more simple quadratics. I really quickly wanted to review with you my method for factoring it when a is actually a number other than 1. So here is how I do it. Do you remember how you're supposed to, when we put these in boxes, and if we were multiplying, we would combine like terms and we would get this middle thing. Well, if we're factoring, we have to undo and figure out what's supposed to go in that box and what's supposed to go in that box. And in class, math 2, we would play a game where we say two numbers, when you multiply them, you get 35, but when you add them, you get 17. And that is the wrong tactic here. Do you remember how we would have a box or something on the outside where we'd say to ourselves, no, if a is something other than 1, we have to take that into consideration. And so I would say that you were supposed to, remember, multiply A and C together and get a 70. And now we play that game and we say two numbers that when you multiply them, you get 70, but when you add them, you get 17. Those numbers can actually be found because you could say that you have a 7V and you have a 10V. And 7 times 10 is 70, and 7 plus 10 is 17. Now, the other version of it didn't work because technically one of these, either the row or the column, is going to be multiplied by 2. And the way that I've written it, you can tell that it's actually the column that got multiplied by 2. And so now we're supposed to take our answers out of these boxes. And let's do that in purple. Why not? Say there's a 2v that goes here and a v that goes there. So you multiply those two things together and you get this interior term. And then here I have a v. V times something gave me 7v. That must have been a positive 7. And then here I have 2v times something gives me 10v, and that something must have been a 5. And just to double check the last thing, 5 times 7 does actually equal 35. So I have now factored this into, ready, 2v plus 7 times v plus 5. Now, you do not have to use my method, but this is how I taught a majority of you. I just wanted to remind you in case it pops up on this homework or in a future homework, you'll be wanting to remember that method for factoring. Okay, so then I definitely did not have you, I believe, as a student when you learned sum or difference of cubes. And you might remember it was something like this: a cubed plus b cubed, or a cubed minus b cubed. And you may have been taught, a method, but I have a cute one and I think it's really appropriate for this time. It's called SOAP. So you're supposed to use SOAP. And what I'll say is that these two things can be factored in the same fashion. Ready? You're going to put an a here and a b here. You're going to put an a squared here and a b squared here. And right in the middle, there's going to be an ab. Now, what you use here is either a plus sign or a minus sign, plus sign or a minus sign. And then right here, we say the last one is always positive. So I'm going to say AP, always positive there. And what matters is which sign do you see here tells you what sign to use there. Okay, so I'm going to, and here. So I'm going to tell you that the mnemonic is ready. It's this: same, opposite, and always positive. So if I'm starting with this, I will use this and that. If I am starting with this, I will use this and that. Okay, same, opposite, always positive. Let's actually do one. And I have x cubed minus 8. And I'm going to say then that a is x and that b is 2, because 8 is 2 cubes. And by the way, you should have realized why it was that I made you memorize cubes back when you were in my room, even though I wasn't covering cubic functions. It's because I had you and I wanted you to memorize them while we had the chance. So I'm going to say that I have, ready, x and 2, x squared and 2 squared, and a 2 and an x. And in here, I'm going to say that the same sign would be a minus sign. The opposite sign would be a plus sign. And this one is always positive. Same, opposite, always positive. I have correctly factored that term. Now, since you haven't had me before, some of you haven't, and you weren't with me in the room when we officially learned this. This is a Math 3 topic, and I don't know if you got a chance to learn it last year. I want to actually take a moment and multiply these things out to prove to you that I am right, and also to prove to you why it works. By the way, 2 squared is 4, so I'm writing a plus 4 right here. And then here, this is my x minus my 2. All right, so I'm going to multiply everything together now. X squared times x is x cubed. 2x times x is 2x squared. 4 times x is 4x. You're like, well, nothing's, there are terms here, Ms. Chatra, that aren't in the final answer. So I think you're doing it wrong. No, double check. Watch what happens on the second row. X squared times negative 2 is negative 2x squared. Aha, those disappear. They're opposites. By design, this is how it works. Ready? 2x times negative 2 is a negative 4x. Aha, those disappear. And a 4 times a negative 2 is a negative 8, which is how we get our difference of cubes. Okay, so I've shown you a cute trick. You do not have to use it. If you have something else that you're more comfortable with, feel free. But you do need to be familiar with sum and difference of cubes. Or I will also mention you could do long division, or you could do synthetic division in order to get this answer. And some people do feel like that's more useful. But when you are doing long division or synthetic division, you still have to come up with that piece by yourself. In order to pick it as a factor that works, you still have to recognize that it is a sum or a difference of cubes in order to know what it is that you want to divide with. Okay? So recognizing that x is cubed and that 8 is the same as 2 cubed is still an essential part. So please review all of your cubes, probably all of them up to 6, maybe even 10, right? Because that would be 1,000. You might need to recognize that 1,000 is 10 cubed. I continually harp on this, that you need to be able to factor this one on site, that this is x minus 3 times x minus 3, which is the same thing as x minus 3 quantity squared. If you were in my room, you should have that memorized. Difference of squares, you need to be able to recognize immediately that this is x plus 3 times x minus 3. Why am I going over this yet one more time? Because I have difficult problems in my AP classroom where, if you can recognize that there's a difference of squares, then boom, you're just able to do that problem without hardly any work at all. So here's the last part of this section where I say to you, is this a difference of squares? And my answer is yes. You're like, well, I don't see anything. There's no squared, right? X is not squared. 4 though, 4 is a square. 4 is the same thing as 2 squared. So can we factor this? So factor x minus 4. Like, no, there's no common terms here. There's nothing that needs to be factored. I challenge you. Think about it. Would that work? It should. I mean, let's multiply stuff together and let's decide. So I take the square root of x plus 2 and I multiply it by the square root of x minus 2. And this again is my box method. I'm using it a lot right now. And I say that the negative 2 times the positive 2 definitely gives me that negative 4 I'm looking for. Here I have 2 times the square root of x and I have negative 2 times the square root of x, and those are opposites, so they disappear. So this is really promising. The question is, what is the square root of x times the square root of x? Oh, let's think about that. That is x squared being square rooted. Yep, you're totally right, Ms. Chatra. That would be x minus 4. You're like, am I really going to be asked to factor like that? No. Well, yes. I mean, you'll see it. It's an algebraic trick that we use to do something when we get division by 0 in a limit. So I've mentioned before that division by 0 is bad and that we can't have that. So we need to come up with some sort of trick in order to find limits when we do get division by 0. And I'll mention that that's why I taught you about rationalizing the denominator. I know that when you were in pre-calculus, you learned about rationalizing the denominator. Please rationalize for me 1 over the square root of 2. Okay, could you rationalize that for me? Yeah, sure. This is going to be what? We multiply by the denominator and we look to see what we get. And what we end up with is the square root of 2 over 2. Yeah, you did that in pre-calculus because you were working on the unit circle. I will mention to you, by the way, that in the AP exam, it's actually okay to leave a square root in the denominator as an answer to like a trigonometric problem. However, that's if you're doing free response. However, if it was a multiple choice answer, you do actually have to rationalize it in order to see that answer having been rationalized it. So that would be the multiple choice answer. And I believe that what we're leading up to actually in calculus is what if I had asked you a limit of something. Actually, let me turn this into a minus sign because then it makes it more obvious. What if I have a limit and I want to know what's happening when x approaches 49? Well, the square root of 49 is 7, and then there's a minus 7. So 7 minus 7, I would get to division by 0, and that would be bad, right? So what I want to do is I want to learn how to rationalize this. As in, how do I get rid of the square root of x? Well, this is what you do. You multiply by something called the complex conjugate, which is the same thing as a difference of squares. Okay? So I just showed you playing around with some difference of squares. I'd like to show you that the complex conjugate is where you have the square root of x, but you just change the sign in the middle, and then you write down that number, the 7. So I will change this, ready, into that. And technically, although it's totally hairy and ugly looking, that whole thing is just equal to 1. And I'm hoping that if I do this right, that something is going to cancel out, something is going to get easier to manipulate for me as a mathematician trying to find this limit. But the reason why I'm putting this into a freestyle is that I actually want to work that out long ways, okay? I want to have a square root of x minus a 7, and I want to have a square root of x plus a 7, and I want to work out my boxes and take some time to do it, okay? 7 times negative 7 is negative 49. And negative 7 times the square root of x is negative 7 times the square root of x. And 7 times the square root of x is a positive 7 times the square root of x. So things are looking really good because in here I now have, ready, something that looks pretty nice, like it doesn't have any square roots. And remember, the square root of x times the square root of x is the same thing as x. I mean, it's x squared being square rooted, which is x. So right here, boom. So I will be able to transform this problem into this. Ready? It is square root of x minus 7 is now this. It's the square root of x plus 7 over the x minus 49. Now, in this case, it turns out it didn't actually help me any. And I wasn't really thinking about it when I made the problem up, so I apologize. But I've already had some recording difficulties, so I'm not going to re-record it. The limit here is still got some division by 0 in it. So there's got to be some other way for me to tell whether or not I have a problem. And this is the moment where I would desperately try to go to a graph. Okay. Now, we do have one other option, which you aren't going to learn for a while, which is to take a derivative. And so we'll see what we're going to do with this later. Okay. But for now, I at least showed you that you can make that denominator look prettier. You can rationalize it. Okay. Now, moving on then to the intermediate value function, I always want to give my own version of it with some real numbers, all right? So I have a 2 and a height of 2, and I have a 10, which is a height of 6. And imagine that you were a blind person. Imagine that you couldn't look at the graph. I could tell you specifically, though, that f of 2 equals 2 and that f of 10 equals 6. And I'm going to ask you a question. Question mark. Is this real thing? Can I find somewhere that the height is 5? If I tell you that this function is continuous. Okay, so that's my question. Is there a height somewhere where, by the way, this number that I need to find, I'm going to call it C because that's the notation we use in the Intermediate Value Theorem, where C is definitely between 2 and 6. It's definitely in there somewhere. But can I find a height where that it is definitely going to hit a 5? And I told you that it was continuous, but I didn't tell you what it looked like. And you're blind, so let's imagine, what could it look like? Well, it could be straight, right? In which case, yeah, I definitely am going to hit a height of 5. It could be like a parabola, in which case I'm pretty sure I'm going to hit a height of 5. How about not a sad parabola, but a happy parabola? What about some kind of cubic? Or, all right, let's just go for it. What if it was some sort of sine, cosine, or trigonometric function that's repeatingly going up and down and up and down and up and down? I'm telling you that if I start at a height of 2 and I end at a height of 6, there is definitely a place where I will hit this height of 5. You can't go from 2 to 6 without going through 5 somehow if you are promised that that function is continuous. Because we know that if it's continuous, there are no jump discontinuities in it. There are definitely no point discontinuities in it. So I will say then that if I was looking at the straight line, it hits 5 right there. If I was looking at the sad parabola, it hits 5 right there. If I was looking at the happy parabola, it hits 5 right there. If I'm looking at the cubic, oh, check it out. It hits 5 3 different times. If it was some sort of trig function, then it could hit 5 here, 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 and I don't know, there. Okay? So, yeah, it's definitely, absolutely going to happen. Yes, it will hit, it will definitely hit 5 as a height somewhere just because of the continuity. And even if you were blind, you would know that that was true. Okay? And that's an amazing thing to be able to state with certainty. That once you determine that a function is continuous, the limit exists from the left, the limit exists from the right, and there are no discontinuities anywhere in a particular interval, by the way, in a particular interval. And for us, that interval is from 2 to 10 on the domain, right, on the x-axis. That if we look in that interval, we know for sure that that function is continuous, then we can guarantee that these heights, that every number in between 2 and 6, that there is a height there. Not just 5, but 4 and 3 and 2.1 and 2.9 and 5.9. Basically everywhere in there, somewhere, there is at least one time. There could be multiple times. There could be a large number of times. Not necessarily infinite, though, because it is a function. It's well behaved, so it's not necessarily going to reach any sort of infinite numbers. There will be a detectable number of times. You'll be able to say, using algebra, how many times. Okay, so we're going to practice more with the intermediate value function a lot in the next couple of days, but that is my freestyle on it. And I'm about to upload this video because I am running out of time.